What's up, man? How you doing? Excellent. Corner.
I'm just going to sit here and stare comfortably at you the whole time. Not breaking eye contact.
I'm used to that.
How's it going, buddy?
Great.
Very, very slow.
You've come out to my selfie meeting. We're gonna, we have several MiSec. We have MiSec, which means
it's fairly easy once you start looking at some samples to really pull out what's malicious, and I'll show you some samples there. And really, if you want to get in-depth in the why, I had a presentation in 2017 about all the in-depth indicators. So my journey kind of began in early 2017, so I presented on general concepts, what really makes PowerShell malicious. And it was really a simple request from one of our clients. Oh, we want to monitor PowerShell, man, you know, detect bad stuff. So I'm like, okay, start looking at it, and it's a huge problem, right? Try to detect, there's so many different things that can be done. There's so many ways to hide your code. There's so many ways to execute code. So many ways to make it look benign or bypass detective controls. And so, so we're going to talk a little bit about that. The first thing I looked at was this cheat sheet from Malware Archaeology. If you're not familiar with PowerShell, go to this and download it. It tells you how to configure PowerShell logging, what to look for, what are some high-profile modules that are executed, things like that. So that's really an awesome resource for ramping up. And I took that list. I mined every malicious module out of there. I created like 150 rules. They were detecting things like crazy with clients performing auditing. But as soon as they started to bypass these controls, it was just easy. You couldn't. You're really struggling to come up with ways to detect the bypasses, and then you start to realize there's an infinite amount of bypasses. So there really needs to be a better approach here. If you guys have any questions, jump into for interactive talk. So really, here's like the list. If you look at the this is just a screenshot of the malicious kind of high-profile modules right here. I created a static rule. And if you guys are familiar with Sims or log management, it's really creating rules like if you see this text in a string, or if this property matches this text, or things like that. So I created 150 around that. I don't know how many there. I think it was like 123, and then we continued to add more. It's probably a little bit outdated though, because I feel like every day I have new malicious modules being created. So you kind of stay up to date, which is also a pain. Like, how do you stay up to date? Monitor Twitter for every mention of malicious PowerShell activity. It's a little ridiculous. So this worked out okay, but it ended up being super noisy. So one thing I learned is that what is best practice not to write, like not to do execution policy bypasses and things like that, is actually very common in many organizations. So I found out that things that I didn't think should be alerting are actually alerting a lot and every day and on hundreds and hundreds of machines. So that took a lot of tuning, and so to even get into a good place, it was a significant amount of work to create the rules and a ridiculous amount of time to tune these rules and see what makes sense. A lot of back and forth. You know, is this situation okay? Is this situation okay? And then finally got to a good place, and we started doing the obfuscation attempts. Just blew all those rules away. So, and then you start looking online. If you follow just a few people on Twitter, the bypass techniques come out daily. So there's all new things, new cradles, new obfuscation techniques, new ways to encode your characters, new way to execute code, things like that. It's almost impossible to know everything there. And so here's kind of an example, right? You can see that PowerShell 1 is super flexible. Just running an encoded command, there's like 12 different ways you can do that. And not only can you just run encoded, you know, -e, -ec, -enc, you could also do like toString and start replacing characters that'll totally bypass any string matching that you're doing. So as I learned more about PowerShell, the more I learned that there's too much to really do that type of rule. So I kind of went back to the drawing board. Here's kind of an example, right? So string matching easily is bypassed by this right here. And this is actually a sample ran through invoke obfuscation. I believe this is really just me writing PS version table, pops up the version. Well, this will actually execute from PowerShell. Right, and so that's crazy. You could create a new rule, looks for environment variables and numbers and string char, but then that's going to generate more false positives, and because some of those characters show up in legitimate code. But when you look at this, so I don't really know Python or PowerShell, like I said, that looks pretty suspicious for many reasons. Look at it; it's just a bunch of numbers that it's executing. Like what's going on there? Look at the string character. The uppercase and lowercase characters are just seemingly random. All the special characters in that, it's pretty shady looking to me, and you know I'm no expert. So I'm going to quickly talk about some of the things that indicate a malicious PowerShell. So you know at this point we said we need a new technique, and we start enumerating the different properties of PowerShell. So you know we know a ton of malicious code. We also know that known malicious activity will often have this. This is taken from a malware sample. And you can see here, look at this. PowerSploit, invoke shellcode, interpreter, persistence, download string, invoke shellcode, window style hidden. Those are all suspicious activity. If you see anything that says shellcode or persistence, that typically means something's bad. So counting up the quantity of malicious, and then also some of those are suspicious, right? Download string, for one, is used in almost every single malicious PowerShell that's ran from malware. It's seen a ton, but it's also used in PowerShell when they're running in an Amazon instance. They're downloading configurations and executing it. So that while that's seen almost everywhere, it's really only suspicious. It by itself alone doesn't indicate malicious activity. And you won't believe some of the things that we see. We see orchestration software running encoded commands. So in essence, it looks exactly like malware. Just encoded command, big blob of base64 code that's getting executed. We also see orchestration software that's doing download string, pulling a script from the internet, and then executing it in memory. Those things are to the T what malware does, but also certain legitimate software. So strange capitalization. Here's another sample taken from malware. Look at split dash split D. So this is a way that they split it up and recombine it to execute it. Take a look just at this alone. Split is capitalized differently 4 different ways. That's not normal. I mean, I'm a bad typer. I don't really type that bad. So, you know, when we're running type, you always want to do case insensitive, but that won't always work. And they're trying to see, you know, people that are working at trying to detect modules by text with a first letter that's uppercase. Obfuscation. So this is just straight obfuscation. This is coming from invoke obfuscation. You can see here, this is really just doing PS version table. So you see right here, so here's the P, SVE, RSI, ONTABLE. That's just showing you the version. But they split it up, they replace it, and then they bring it back together and execute it. So that's a way to bypass any type of mechanisms. Ratio of special characters is another one. I don't even have a clue what's going on here. But look at all this. Replacement. You see some known malicious modules, but like this is some crazy encoding and execution. So anything like this is pretty bad. Cosine Similarity. This one gets a little bit out of my realm. This is kind of you're detecting how similar an event is compared to known good events. So I create a long list of known good events. These events we've reviewed, you know, thousands of them, and we take an event and you can compare it to the text. And so what you see here is that what you do is you split. You're doing character frequency analysis. So on this left here, where it says terms, these are all the terms that exist in good log 200 and good log 7. And you see D1 is the first event, and these are the quantities you're observing of those characters, and D2 is the second. And so it's doing analysis on it, the cosine similarity, and saying how similar is this. And what we notice is that known good events will typically be above an 84%. So here you see 94. This a good log versus a bad log is about 71.
What language is that?
This is in R. So my background is primarily in Python and R. So I like R a lot from a statistical analysis point of view. It's probably the best for data visualization. It's probably the best. I work in Python because it interfaces with a lot of my coworkers and stuff a lot better. So cosine similarity is built into R. A lot of statistical tests are. So yeah, so that's one. And what you notice is when you see those crazy events, like you see here, this cosine similarity will be super low when compared, because this looks nothing like legitimate code, right? What classification is, how do you train a model, what is machine learning, things like that. And kind of, this is essentially, once the data is processed, it's like the hello world of machine learning problems. The data is just that good, though, so it ends up working out. So what is a classification problem? It's taking those events, converting them into predictors. So we got like 7 predictors. The uppercase to lowercase ratio is a number between 0 and 1. The alphanumeric alpha to total character ratio is a number between 0 and 1. So you calculate for the raw text, and you just store it in a list. So it's a comma separated list, and I'll show you what that looks like in a minute. They're able to take new, previously unseen events, feed it into the model, and it'll say this is suspicious or not suspicious. So there's tons of tools out there. I use scikit-learn. Has anybody heard of scikit-learn? It's one of the most popular ones. It's written in Python. It's super well documented. They use it in production in some organizations. We end up moving away from it into a tool called Keras, but that's more of an engineering decision than accuracy or tool decision. But go ahead, take a look at it, scikit-learn.org. You know, they run through, there's tons of documentation out there how to use it and go through a training model. So at first I used a tool, I used Canopy for my Python IDE. Canopy is kind of like a, it has all the scientific packages installed already, runs on Windows. I find some of these packages are difficult to install on Windows. They install great on Linux, so everything will run on Linux just fine. So if on Windows, Canopy works great. I moved to Jupyter Notebooks. I find Jupyter Notebooks to be super easy to experiment with. You can move cells around. You can run code chunks. You can document it in Markdown, save the notebooks, load them for other people. It's really a great tool, and that's what I would suggest using. In R Studio is awesome. You could use that as well. And really my background, so I'm a security practitioner. I've been doing logs my whole life, but really for the last 3 years I've been trying to ramp up in kind of like data science, data analysis techniques, because I feel like if anybody here is in log management or log analysis, this is where you're going to have to be. I mean, we're pulling ridiculous quantities of data now, far more than we were seeing even when I started. So like 7 years ago, we'd have a SIM, have about 3 terabytes of storage. Now, I've deployed for clients SIMs that have 40 terabytes of storage, and that's in a base unit. Not even let alone the expanded. So people have petabytes of full packet captures. I myself, I have access to like a petabyte of pure log data. So we're getting to the point where there's a gold mine of data, and no one's really effectively using it. So that's where I kind of set out. I focus on data analysis with Python and R. There's tons of data. I do the data science specialization in Coursera. It's pretty cheap and super valuable. So if you want a good resource for actually learning machine learning and easily, machinelearningmastery.com. They have data sets. They provide the methodology, all the tools, and you can just run through it. I installed Canopy, went through an example there. It's very easy. The hardest thing of anything is preparing the data. So, I can make them available, yeah, probably. So, no, I wouldn't. Yeah, I'll make them available for you. So, yeah, there's a lot of resources. At the end, too, I kind of like put the resources. I don't know if I added Machine Learning Mastery. That's a great one. The guy has machine learning techniques in many different languages, time series analysis. If you look at log data, it's all time series data. That's an area I haven't explored significantly. So, but the hardest thing by far is getting your data and preparing it in a way that's suitable for a model. But once that data is available, it was pretty. I was amazed. I was like, this can't work as good as I think it's as well as I think it's going to. I remember running through my first model, checking the accuracy numbers. I'm like, this is sick. This is way better than I thought. And when we tested against data we haven't seen, which I'll show you, it performed very well. So here's the problem, or the process, not the problem. Define your problem. Having a clear definition of what you want to do is paramount. You see all this stuff out there. Machine learning. We use artificial intelligence. Brains everywhere. Most of the time, you really have no clue. And I've sat there and asked, like, what are you actually doing behind the scenes? And they're like, we've got equations, man. We could show you, but it would blow your mind, right? So, and I'm like, I kind of want to know, but I also don't want to push the subject. So anyway, that's not very well defined for me. What's the process? What's the goal? And how are you using it? Because there's also a lot of problems with machine learning, and if you're too vague, if your data is incomplete or incorrect, there could be a lot of issues. So having a clear problem set is required. So getting and cleaning the data, that's the next hardest thing. Like, how do you get the data? And for me, that's the hardest part, right? I've got tons of data available to me, but trying to pull it gets pretty difficult. It's scattered throughout the world on many different places. So getting a good data set is very hard. But once you have it, things get a little bit easier. So once you have it, you can evaluate algorithms pretty easily. And I'll show you. I don't really know the pros and cons of each machine learning algorithm. So I just ran it through 12 different ones and it spit out, here's the best accuracy. Here's what you can use. We'll present the results, right? So a lot of this I did on my side at the very beginning in like my free time. And I presented the results and I'm like, dude, this says it's 99.5% accurate. And they're like, no way. So we started pumping it through data and it came out, it was correct. So we did have a lot of tuning to do. Even at 99.5% accuracy, we'll talk about how that can be a little bit misleading, but we had to tune. And like I said, once we start seeing new data we've never seen before, having a wider scope of data, you start to say, okay, at this place, they never do execution policy bypass, but 99% of other locations, they actually do. So, some of these things would trigger the model, and we'll talk about that kind of at the end. So define the problem. We talked about this, right? classify PowerShell events using high-level properties. So the high-level properties are things like uppercase to lowercase ratio, quantity of suspicious modules, quantity of malicious modules, and in a manner that generalizes across anywhere, right? We don't want this to be specific to your organization, although that'd be fine if that's all the data you have, but you want this to generalize as much as possible because you don't want to hand engineer things. You don't want to be fiddling with the model day in and day out, because then it's kind of pointless. You might as well have a rule set. So my data comes from Windows logs, primarily command line logs. Those were the easiest for me to get access to. So like from the Windows command line, you can see 4688. This is, I think, enabled by default in all Windows environments. Down here, the process command line. So here's an example. I'm just showing the PowerShell version. PowerShell.exe PS version table. But if that was longer, it would be, download string, malicious.com, pipe it to invoke execution, things like that. So that would show up as well. This process command line, at one time, you had to apply an update. I don't know if that's done by default now. So you would have to take a look at whether that's enabled in your environment or not. You had to apply like a certain update and then enable a configuration command to enable that for your environment. I believe that's also documented in the malware or the PowerShell cheat sheet.
You can also push it out through your GPO.
What was that?
You push it out through your GPO.
Yeah, so definitely, yeah. If it's not enabled, it's just a push out through GPO. I find that in some organizations, a GPO change is more difficult than others. Even no matter how to configure PowerShell, they go step by step there. Microsoft has some TechNet articles too, so it's pretty easy once you follow it, and if you have step by step directions and fairly good administrators, shouldn't be that much of an issue. So getting and cleaning data. So this is the key step in any problem. Like I said, the hardest thing by far. So I started by reviewing a large quantity of PowerShell events. I split them up into two files. I split them up into one file. These are raw events. I split them up into a good file and a bad file. And so I got these events from various places. You'd be surprised how often people are posting them on Twitter. I had, at the end, I'll show you a place where you can download like 15,000 encoded commands from Palo Alto provided it. And they have it on GitHub. I downloaded as much malicious software from VirusTotal as I could, ran that through Cuckoo, piped that into just a syslog server, saved it off and analyzed those, and then just pulled legitimate files from anywhere. You can get it from your organization, from your clients, or wherever you're at. But basically, I went through those and started just separating those into a good and bad file. And for each event, I calculated the vector values. The ratio of uppercase characters to lowercase, like I showed you, the ratio of special characters to total characters, the ratio of alpha characters to total characters, the cosine similarity, the count of suspicious modules, and the count of malicious modules. So the suspicious modules versus malicious modules are kind of there because certain modules you'll see, like if you see persistence or shellcode, that's bad. But if you see download string, that's pretty bad, but there's also a lot of legitimate use cases. Encoded command is used far more legitimately than I had ever previously thought. So I started realizing that I had to have two different counts because, the more suspicious you see, the more bad that event probably is. But at the same time, it's not as bad as if you saw PS attack or power exploit or things like that. So this is kind of what a record looks like. So from here's a sample event. You see, this is just that obfuscated event I showed earlier. I created a Python function. So basically, I say, I derive the count of uppercase characters. I derive the count of lowercase characters, and just did total upper divided by total lower. Right? Pretty simple. I have the code if you're interested. I didn't know how to do it, so I'm Googling, right? How to count uppercase characters, how to count lowercase characters, right? And so I just figured that out. Same thing with special character ratio, the alpha character ratio. The cosine score was pretty tough, but if you look at Lee Holmes there, he shows you how to do it in PowerShell. And if you just Google Stack Overflow, or if you just look in Stack Overflow, there's tons of samples how to manually do the cosine similarity. And there's also, built-in tools in most things like I think in NumPy and R and things like that. And then just counting the suspicious modules. So for each event, I'd run through a list of known bad, say how many exist. I just use regular expressions in Python. Say how many times is this text seen? How many times is this text seen? And just add those up as time goes on. And the same thing with malicious modules. And then finally, you got the labels. So the label's 0 or 1, right? So 0 is benign, 1 is malicious. Just because, in the classification, I thought at the time, it was over a year ago, that everything had to be in numbers. You can have categorical variables too. Like you could have plane, car, or whatever. But I think typically it's better to have integers or numbers of some sort.
Real quick before you move on,
yeah.
2 questions. One, were you counting spaces in the number of your total characters?
So that I'm not quite sure. For uppercase, lowercase, definitely not. Special character ratio, I believe I was actually. Alpha character ratio, I believe I was. So yeah, I'm pretty sure. I remember thinking that at the time, and I don't recall what I did because one of the properties that we noticed at the time was that when you look at malicious code, especially in script block logs, it's super condensed, right? There's no spaces really. But when you look at real code, there's carriage returns, there's new lines. People are writing functions and they have them spaced out over. It's not just a one-liner. So I remember thinking that. So I'm pretty sure that we did to some extent. So I would think that matters.
Second question, your cosine similarity. So you have your malicious event. What were you comparing it to?
So I had about 4,000 benign, known, labeled good events. So what I did, and I'm not positive, the way I did it, which I think there's better ways to do it, is that I would take that event, compare it to each one in that list, and then average that out. And that's where this number is derived from. But what we do now actually is that you can create a document term matrix of all of your good events in conjunction with your events you're testing, and then it'll instantly tell you. So I kind of did it a hack way. The data, I don't know if the data is exactly the same, but when I tested when I was looking through the cosine scores, there was, like this one, for example, shows a 0.36. That's super low. Anything under 0.7 is suspicious. So, and if you look at most, like the scikit-learn framework has those things built in, so it's actually pretty easy. Jason.
Do you have one of those like super special total accounts to be able to download?
Yeah, so we did. Yeah, and that's good. That's one of the things where it's hard to get data, which is also why I linked to the Unit 42. So while I do, right, I analyzed 400 pieces of malware. Of those 400 pieces of malware, many of them were the same or almost exactly the same, right? So they're shown by hash. So if they mutate or change even slightly, the hash will be different. And so I noticed that the logs that I get were almost exactly the same in many cases. So I think that probably was about 200 samples. And so the Unit 42, although it's all encoded commands, which I didn't like because we don't always see encoded commands, the decoded portions they varied pretty significantly. So yeah, getting your samples is tough. But the thing is, too, if you're running this in your own organization, you also have a lot narrower scope of activity that's actually going on. So I don't know whether, like, you're trying to find out what's suspicious and what's not. I don't know whether that would make a big deal or not. And also, we generated a ton of data. So I went through invoke obfuscation. I followed the tutorials and just basically tried to generate the widest and most diverse set of obfuscated data as possible. So it was kind of a combination of many things.
In your adventures, you said that you were able to deobfuscate and find a number of these different payloads. Have you come across any specifically that you know for a fact were created with Empire?
Yes. Not using Empire. Well, I don't know about Empire. Using those frameworks for sure. And I'll show you in that one that I showed you where I showed Interpreter and all that. That's pulled directly from GitHub. So some of this malware just just downloads the raw code from GitHub and executes it, right? So these are, like, some of these guys that you see on Twitter, their names are kind of like an IOC because, like, you should never see that person's Twitter handle in your logs. And so, there are lots of cases where you'll see that, right? And so, let's see, I'll pull that up right here. This one right here. So this one right here, so this is definitely using Interpreter.
PowerSploit.
Do you see PowerSploit in there? Yeah, look. Yeah, right. So this is code, whether it's downloaded from GitHub or copied or whatever. This is using those frameworks for sure. So using those frameworks, although it's kind of like, okay, you don't want to do that as much, the real malware is using it. So where are we at there? Okay, so this is kind of like what a record looks like right here. So I split this out, but it's really just comma separated text file that I had, and this was split into good and bad. So here's kind of like a big conversion of what it looks like. And this is all the file is. This data set's online too if you guys are interested. And this is just PowerShell metadata, so there's nothing like specific here. This is all derived values from my own functions provided, and it works pretty good on the data set. So here's a sample malicious event with the calculated predictors. So if you see here that I have a function called genPredictor, that's just a function that goes through, reads the raw event, and calculates these values right here. So the I forget what order these are in, but this is suspicious modules, malicious modules, and here's the actual event. One thing for this one, I just learned that this IP is actually like a Cisco test to see if like your web blocking is working correctly. So that was interesting. It's not actually malicious. Huh?
Malwarebadguys.com?
I think so. I don't know. Is that?
That's the umbrella test.
Yeah, I think it might be because there was when I searched malware.htm on Google, it was a Cisco site, and they had like multiple IPs and different ways to test their blocking stuff. And I think like OpenDNS does similar things, and so this actually really isn't a malicious. This isn't a hacker, but this is exactly what they do. But anyway, here's the derived values for this event right here. So one thing to keep in mind, I'm trying to get everybody to understand, the machine learning process and really hopefully be able to apply it to other problems. Because everything I'm doing here is not ideal. We ended up going a different route, which I'll talk to you about the end. This does work very well, but like with the suspicious modules, malicious modules, that's to be updated over time, and that kind of sucks. That can be done, and it's easy to do, but every time you update the list, you got to recalculate these values on your data set. So just keep that in the back of your mind. You won't be able to copy this exactly, but I think that you'll have enough to kind of, if you're interested, implement this. Jason?
Have you seen any, and maybe you've been talking about this the whole time, I don't know, have you seen any key-based style obfuscation? So you're saying that they're doing codes and such. Historically, going way back in the days, we've always seen like these strings and, WordPress attacks and such, and they'll do like an encode to MD5 hash, and they'll supply a numeric or otherwise alphanumeric string to de-obfuscate that. To run things. Are you seeing that?
Absolutely. So, like, if you look at invoke obfuscation, there's one technique using RSA encryption. So when you look at that, it actually just encrypts it, and that's what you're trying to execute. Passes that to the decryption key and executes that kind of bunch of code. I don't know if I've actually seen that specific one. I have seen things where so it's like base 64 encoded, but it's easy to detect and decode. They would every like 8 characters would be a split character, so it'd be like a forward or something. No, actually, it was like the one I saw was binary encoding, so it'd be all in binary, and every 8 characters would be like a forward slash, a comma, and then they would provide a key at the end and say, split by these 12 different characters. So you'd have to split it, and then you convert that to ASCII, and then you execute that in memory. So it's kind of like it's providing the key. Well, it's not true encryption. It's providing a split key. It makes it a little bit more difficult. So, okay. So here I just the genPredictor is just a function. Pass in an event. So here's mail events 8, which is this event. The malicious modules is a list of malicious modules. So this is what do I want to be considered a malicious module? What do I want to be considered a suspicious module? And the good events. So the good events is used to calculate the cosine similarity, which is right here, 0.65. So this one's pretty low. Anything under 0.7 is suspect. But some known good is can be that low. So calculate the predictors, process the files, and then you just combine the files. So here, I'm kind of going to walk through the actual code that I ran through. This is in my Jupyter notebook that you guys can go look at and download and run if you wanted. So here I'm just saying, here's I'm putting all the data into a variable here. I'm using the first 6 columns, and we're going to use that for processing. So at this point, we're pretty much almost ready to start experimenting with the models, right? So we've got the 7 columns of the predictors. We've got the labels. So now we're going to separate the calculated predictors from the labels so we're going to separate the labels and the data because we're going to be doing some experimentation. So I'm going to separate the actual labels into, or the data into the X variable and then the labels into the Y. You can see here, so here the values of these predictors are going to be everything in my data, and I'm using column 0 through 6. The labels here is just going to be the 6th column. That's just the 0 or 1. So that just indicates, is this malicious or is this benign? And here's an important thing we're going to do. We're going to generate it in the train and validation data set. So when we're going through this, you can't test your model on the data it's trained on, right? Because you're always going to have a high score when you do that. It's kind of like a #1 thing. Because you're gonna get that, you're gonna train it on the data, and when you try and test it, it's gonna come out 99% accurate every time. But as soon as you start feeding it event from the raw events that are coming from your environment, it's gonna score very badly. And it's kind of like you're taking a college math test, and they got 2 versions. You somehow got version 1, you memorized it, but then they happen to give you version 2. You're gonna just bomb that test, right? It's a similar concept here. So here I'm just saying. Validation size is 20%. So I'm going to save 20%, set it aside. After we develop our models and do some training and tweaking, we're going to see what type of numbers we get on data it's never seen before. Seed, this is a random seed. One thing to keep in mind is as I'm going through this, every time I run the same data through the machine learning models, the results will be slightly different because there's just like a certain amount of randomness in those algorithms themselves. Setting the seed to 7 is kind of giving it kind of like a repeatable process, but I still see the numbers change. So I don't know exactly what that's doing. So here's what I'm doing. I'm creating the X train and X validation. So this is the training and testing set. This train will be 80%. This will be 20%. The Y train is the 80% of labels. The Y validation will be the 20% of labels. And here I'm using this. These are tools provided by Scikit-Learn. So model selection, train test split, and basically I'm just saying take X and Y, split them into those. Test size is the 20% right here, and then the random state is the seed. So you're kind of specifying the random state for reproducibility. I think that may be just for the randomness, the way that it randomly splits this into 80-20. So, and then here I'm printing the X value and the Y value. So what I'm saying here is we've split it. Here's an X record, so this is just the data, and here's a Y record, just 0 or 1. So now at this point, I started evaluating algorithms. When I look at this, there's a whole bunch of algorithms, and you start looking at random forest classifiers and how they do in the background, super difficult, and that's just one of like many different types of classification algorithms. So I wasn't quite sure what to do. Each one has pros and cons, and I found out some of the stuff I did was not quite. I'll talk about that at the end. But what I did is just piped all the data through all of them and see which one was the most accurate. Different algorithms will work better on different types of data. Does all the data need to be between 0 and 1? Can you have categorical data? In certain types of problems, one might do better than the other. So here we're going to go. These are the ones that I've used, and now we're going to actually test this, right? So here I'm going through I'm going to evaluate the accuracy of each model. And what I'm going to use is a k-fold split. So in our train set, I've got 80% of the data. But I also, in that data, if you kind of want to test it. So I end up splitting that data into 80-20 as well. And it's actually 90-10 to train on the 90%. Then testing the remaining 10%, and actually do that 10 different times, and then average all those values together to kind of get a better understanding of the accuracy of that model. Because we are not going to test the train on the validation set, because we're going to save that for later. So here I've got a variable called models, and all that does is have random forest classifier as one value, and then I give it an RF, a shorthand descriptive term, for the other. So it's saying for the name, RF, and model, which would be random forest classifier, in the models variable, we're going to do all of these actions. So here I'm saying I'm defining the fold criteria. So again, this is part of scikit-learn. I'm saying let's split it up 10 times. I'm going to use the same seed I used before, which is the random seed that was set to 7. So now I'm going to use the model selection, the cross validation there. So you're going to feed it the model, which is the model will be one value, such as random forest classifier. X training and Y training is the training data and the training labels, because it's going to learn off of 80 or 90% of the training data, test it on and get the accuracy on the remaining 10, and do that 10 different times for each one of these. So then once we develop the, we're going to use the k-fold. So that's setting this k-fold parameters right here, which is essentially just saying split it 10 times and do it 10 times. And what types of scoring are we going to use? So here the scoring variable is accuracy. So scoring really is like a different type of metric. So we're going to talk about this. What's the difference between accuracy, recall, precision, and why we would care about the different types of metrics to gauge the model by. So we ran through there and just print off the results. And here you see that on average, out of the 10 times that we train and test the data, for random forest it was 99.7% accurate. For linear regression it was 99.5. Did pretty good on all of these. So one thing I learned is that some of like my data, the way I had it prepared, was not very good for some of these. Like the naive Bayes was not very good. For linear discriminant analysis, the way I had the data was not very good, because I had values like accounts that could have been like 16, and it's better to normalize some of the data, which I'll talk about a little bit later. So each model is evaluated using 10-fold validation. The training data is divided in 10 parts. And we'll do that 10 times. We'll train on 9 parts, test the accuracy on the 10th. So accuracy is the quantity of true positives plus true negatives. So divided by the total sample. So how the ones that we guess right, the ones we correctly guessed were benign, and the ones we correctly guessed were malicious, divided by the total amount. So the accuracy is pretty good. It can be a little bit deceiving because our data, 90% of the data is benign, and 90% of the data is, and 10% is malicious. So if we guess benign on every single one, we'd have an accuracy of 90%, which actually sounds good, but is as bad as it can possibly get. Here's kind of a picture of what k-fold validation is. So here we have 5 sets. We're going to save the first 20% for testing. We're going to train on this, come up with the accuracy. And then we're going to test on this second part and use the remaining for training. And we do that 5 times and average all the accuracy out. So here's just kind of a plot to show how our different algorithms did. This is a box plot. This line here is the mean. So you see here, random forest did well, linear regression did okay, k-nearest neighbors was pretty good. The decision tree was pretty good too, but LDA and naive Bayes were very low. And I think that was because of the way I formatted my data. But at this point I didn't really care much because I'm like 99.7%, I'm like, that's awesome. I'll take that all day long. Well, we'll find out it isn't that good. I mean, it was way better than our rules-based processing, and we were able to make it a lot better in the end. So yeah, it's not always the best measurement though. If it's heavily biased, so in my data set, if we said everything was benign, we'd have 93% accuracy, which sounds pretty good, but that's truly not. So depending on your case, you might look at other scoring metrics. So we're going to talk about precision. So here I do a different scoring measure. This is called precision. We're going to run through that. We're going to do the same process, average it across all the data, come up with the precision. So what precision shows is the percentage of positive, suspicious, or positive predictions, so suspicious events that we got right, that were truly suspicious out of all the predictions. So every time we made a guess, how accurate was that guess? So if you think, we could have 100% precision, but our algorithm could still suck because we still missed. So while every time we guessed it was right, we still could have missed thousands of pieces of malware. So that's where this kind of shows you. And this kind of says what percentage of suspicious classifications were truly suspicious. Jason?
From a human perspective, how are you doing the validation on that? So are you actually just going through and outside of these algorithms, outside of this process, and then going as a human? I know for a
Yeah, so the data that we provided has already been cultivated in that way, right? So every piece of data I know is bad. I personally, or my partner, somebody that I trust, that has reviewed the data and said this is malicious and this is benign. So does that answer your question?
I guess it does. I mean, maybe I'm overthinking it. You know, for me, I'm just trying to understand beyond a shadow of a doubt, right? So, you know, false positives, false, you know, whatever.
Yeah.
You know, I'm just trying to go probably
No, that's, I mean, so one thing to keep in mind with these algorithms too is, and this is why sometimes machine learning is bad, is you need to be able to explain your results, right? So, you know, we're essentially feeding a black box with events and saying, oh, this is suspicious, this is benign. We don't really know exactly, although we can come up with reasons, and we'll talk about that maybe after a little bit. So, and things that I'm doing to be able to explain it. And so we keep metadata, like, so in this event, you know, this was a probability of 96. The algorithm says there's 96% chance it's malicious. And in this event, it contains these terms, which are seen in 40% of malicious events that we've previously seen. And so we keep data like that. And so we're able to explain it. Also with PowerShell, if we were just to see the event, you can pretty quickly tell in PowerShell that it's malicious. It's just with minimal expertise, myself, because I don't code in PowerShell. I'm not a pen tester. I've reviewed a lot of logs, but so with minimal expertise, I'm able to determine very quickly what's malicious and what's not.
I think you just answered what I was trying to unsuccessfully ask.
Yeah.
Is it giving you some sort of output that, you know, where you explain that it's giving us some terms that it feels suspicious?
Yeah, so when we give it a label of 0 and 1, these algorithms can also pop out a probability, right? So that's one thing that we've changed too, is that there's a threshold. So by default, if it's above 50, it's going to say this is malicious. If it's below 50, it's going to say it's benign. But, you know, really we could say just show us the probabilities, and we'll only consider this benign if it's below 25%, right? We care more about detecting bad stuff, even at the expense of some false positives, because missing one event is very significant, right? But at the same time, you don't want to have alert fatigue. But I'll talk about some of the results that I've seen. But in the end, this was, you know, we've reduced significantly the amount of false positives that are being reviewed, which is way less time. So if we can dial this down so it's using more false positives versus false negatives, we're fine with that.
I'm just kind of wondering about your algorithms. Are they sort of transparent? I know that's one thing that we're listening to machine learning. Do you understand why it's doing what it's doing?
So most of them, no, not really. Like random forest, I definitely don't. If you look at the CART algorithm, that's actually a decision tree. Decision tree, you can print out the decisions that it makes, right? So it's essentially a rule-based system. So maybe if you're like, I have to be able to explain this, you could use the CART algorithm. It could you could use a decision tree, which you could essentially create, have the algorithm create rules for you and implement those rules. And then, like I said, we keep metadata on a lot of the events, so we know that these terms are typically bad, things like that. So why it's happening, we're not, like, in some cases I do, some cases I don't. So yes, so this is precision. So what percentage of suspicious algorithms are truly suspicious? So yeah, basically, of our suspicious predictions, how often are we right? And like I said, we could have 100% precision, and our algorithm could be totally junk, right? And it depends on your problem. Maybe if a positive prediction, so if I say, okay, we're going to predict this is malicious, this triggers off a 60-hour investigation. In that situation, and that costs 4 professionals involved, so in that case, you probably always want to be right. And in that case, you know, you'd want your precision to be higher. But for me, most of the time, I want to catch as many malicious events as possible. That's kind of where we look at recall. So recall is, you know, how much can we trust the algorithm to catch all of these suspicious events? And that's really more important to me. So what percentage of truly suspicious events were classified as suspicious? So you can have a very good precision and very horrible recall because you're missing a ton of malware for whatever reason. I went through the same process. You see that I used the recall scoring method. Here's the recall. And you see that random forest has a way different recall so it's a little bit lower. And all of these start doing way worse in terms of recall. Linear regression, The indiscriminate analysis is really bad there. So you can see the different algorithms shine differently when it comes to recall versus precision. Here's kind of a picture to show. It's kind of hard to figure out the difference between precision and recall. And so here kind of shows you, right? So here's all the true positives, so truly malicious. Here's all your false positives, the ones you said, these are malicious, but they're actually benign. It's administrative activity. These are all the actual benign events, and these are all the actual false negative events. So the precision, is the true positives divided by everything that you can, the total quantity that was predicted as positive. Then recall is true positives divided by all of the malicious events, and so that kind of gives you different pictures into your scoring mechanism.
So which algorithm did you guys end up settling on?
Well, we try to maximize these. We don't. This isn't an algorithm. This is really a scoring mechanism. What algorithm did we end up spending on? So at first we used the random forest. Random forest was pretty good. Had high accuracy, pretty good recall. It was pretty resistant to our data was very different. So random forest works pretty well when you have different types of predictors. I have 16. I have a count that could be 16 or 0, and I've got a whole bunch of ratios, and those are from 0 to 1. Where some of them are gonna weight your counts much more heavily than your ratios because they're higher numbers. And so we end up going with that for a while, and I'll talk about it at the end. We end up switching to a different algorithm. But if you look here, random forest did pretty good. It's got 96 recall, 98 precision, and the overall accuracy was 99.7. So
just so I can try to understand recall, so you're getting 96 out of the 100 malicious code, right?
Yeah. So
if
they're
missing 4 out of every.
Yeah. And for this, and keep in mind too, this is the data. This is my very first data set that I derived from the samples. So our samples were very limited at this time. Also, what we used for values for suspicious and malicious modules was tweaked significantly following this before we implemented it into our production. So this is a little bit lower. We ended up doing a little bit better. I mean, not a ton better, but we were able to improve this a little bit. Finally, we have an F1 metric. So you have precision and recall. But if you want to mix, the F1 metrics kind of shows you a mix there. So you saw for random forest, recall was 96, precision was 98. The F1 is 97. So the F1 score is really the precision times the recall divided by the precision plus the recall times 2, and it ends up being kind of a blend of those two. So that's just another scoring metric. And I think there's a lot more metrics, and depending on your algorithms too, if you're looking at clustering versus classification, there's different ways to determine it as well. We're doing binary classification, malicious, not malicious, but maybe you're doing cat, dog, elephant. That would be a different type of classification problem. So here what I said, random forest algorithm was the most accurate of our testing set. The validation set. So here we've only been working on the testing set. At this point, we need to feed it data we've never seen before, right? Because our accuracy is derived from tenfold validation. We're still training on each one of those folds. We're training on much of the same data. So we need to feed in new data to see how is it really going to act in a more realistic data set. So keep in mind, never train your model on your validation set, because if you're testing accuracy on your trained portions, it's going to be way higher than it should be. Just like I said with the memorizing tests. Version 1 and you get version 2 of the test. So we're going to train the model to test the accuracy on the validation data. So here's kind of what I was talking about. So here's where I'm taking the training data. I'm creating the model. So I'm using the random forest classifier right here. And this is the extent of the data right here. This is creating and testing the entire machine learning model right here. So we're saying we're going to use a random forest classifier, RF. We're going to fit it to the X-train and Y-train data. So the X-train is just our records of the different ratios and counts. The Y-train is the labels. And now we're going to do the prediction on the validation set. The X validation is the data that's never seen before. And all you do is say rf.predict X validation stores that in the predictions variable right there. That's it. We've just essentially classified thousands of events. This takes about 3 seconds or 4 seconds to do all of that, and then we're going to print the accuracy. So here we have the accuracy score for Y validation, prediction. We're going to print a confusion matrix, which I'll talk about in a second, and then a classification report. So here in this attempt on the new data, our accuracy was 99.8, which is actually better. This though, keep in mind that I added the slide a little bit later, so this was kind of on was a different run of the algorithm. So I'm not positive that the data that was being trained and the data that was being tested is the exact same training and the exact same testing data from previously, but essentially the score is the same as from our training set. Here we have a confusion matrix, and this shows you exactly how many we predicted successfully for malicious, how many we predicted successfully for benign, how many we thought were malicious but were actually benign, and how many we thought were benign that were actually malicious. So this is a confusion matrix right here, and this is kind of just to show you what this is. So the row is true benign, so we have 1,565 correctly classified benign events. We have one that's benign that we classified as malicious, and then down here we have truly malicious events. So we have 2 that were truly malicious, but we classified this as benign. So this is really the worst right here, and the hardest to find, false negatives. And then we had 117 malicious events that were correctly classified. And then here we have precision, recall, the F1 score, and then this is just the raw numbers. And so it averages. So it also tells you, for the 0 and for the 1, splits it out between, our guesses for malicious and benign. So here we see true positive, false negative, true negative. The hardest thing is determining false negatives, because how do you know what's bad that you don't know is bad, right? So this gets pretty difficult, but luckily we have the virus total subscription. So the thing we're constantly doing is we have a subscription for PowerShell events coming from virus total. We pull it down every time a new one's seen. We run that event through Cuckoo Sandbox, develop logs for it, feed into the algorithms, and we know pretty much if it's coming from a piece of malware that it should be bad, right? So we should always classify that as malicious. If we ever see anything that's a log that comes out of that we classify as benign, it gets emailed to us immediately for review, because that's a false negative. We wouldn't normally know that, and so we'll take a look at that. A lot of times we'll see data we've never seen before. We had an example like a piece of malware that came out of virus total. The log event did some stuff we hadn't seen, and what it did was it executed Internet Explorer and sent you to a web page automatically. And we're like, wow, we haven't seen that before. But it kind of makes sense, right? Because if you want to send them to, you want to automatically send them to somewhere, it's like a fish gate, tell them to enter their domain creds or something. So we're not sure. We looked it up, we did some research. It was actually sending them to a pen testing site from Germany. And we kind of think it might have been like this guy's business card, right? Like if you're looking at it, he was selling services at that point. And I'm like, what is this, right? And so that was kind of interesting. But that was a method we'd never seen before, and we added it to the training set following that.
How are you testing benign code against this? Like, how do you know that the
we have
code is?
So the one thing, so I guess we're taking all of our benign events from customers and putting it in. We only add training set that we've personally evaluated. So if it comes through as classified benign, we really don't do anything. It could be classified as benign and ends up being malicious. We could detect that. So a lot of this, when we have multiple solutions in play, right? We have network appliances, we have EDR solutions, and our log data. So a lot of times we'll have multiple alerts come off from the same thing. So we do look if there's an alert from something like Carbon Black or antivirus, and it's PowerShell related, we'll go back and check this. We've had that like one time that we've actually picked up. But that's really it. So there is the possibility that it's malicious. We're classifying as benign. That's really a false negative though, and we hope to catch that through virus total. So that's really the best way. If it's truly benign and we classify as benign, we don't care, right? Because that's correct. So.
But do you need to gauge a ratio to figure out what score is benign versus malicious? So you use training against benign data to figure out what benign data score is?
Yeah, so the benign data and malicious data is all part of our training set. So yeah, so it already is that there. And so the score is the accuracy score, how well our model is doing. The classification has its own probability threshold, but that's a little bit different, right? So we don't really, we change that, but it's kind of that's the probability of being malicious versus the probability of being benign. And so we alert on things at like 25% rather than 50%. But that's a little bit different than the false positives and false negatives there, I believe.
Couldn't you also say that since malicious code is going to be highly variable because they're always trying new tricks for obfuscation, but benign code is generally expected to be well written, well behaved, and have certain characteristics, which is what you're checking for. It's less important to train on new benign as it is to train on new malicious.
Okay. So I think that probably answers your question a little bit more than the way I did. So you're absolutely right. And so, in those cases a lot, you're right, like formatted code looks very similar. And when you look at it, so while terms may not identify that malicious code, the cosine similarity would be very well. You can get super crafty, do crazy obfuscation. That's going to still show up like a red light in your cosine similarity score. So yeah, that's a very good way to put it there. I think it's the same. Okay, so random forest at the highest. So here we did. This is the accuracy on the validation set was super high. So we're like, okay, this is cool. And this is really what we started to use at that point. So this is what we used for a while. We did a little bit of tweaking because once we started getting a larger data set, we realized that certain terms are being seen legitimately that we never thought would be. We started discovering things we didn't know. But the algorithm, it was very successful off the bat, even if it wasn't even optimal. We reduced false positives significantly from like 3,000 to like 5. We increased true positives. We could tell we ran it in parallel with our other solutions. So the true positives increased. We decreased false negatives because we could detect this because we're running in parallel with existing rules. So our other solutions weren't catching things that this wasn't catching. And we're also running this in new virus total samples. So we feel pretty good there. So now here's just an example of how to make predictions on previously unseen data. This is kind of what you might be interested in, right? So you're like, well, okay, so it's easy to create a model. I just got to get the training data, label the data, calculate these predictors. What do I do then, right? So you just feed it an event. So here's X validation. This is the entirety of our data set. Here's just one event, though. Just pass it to RF predict. It expects a certain shape. That's why I reshaped it there. And so here you see we're printing the event and we're printing the label. So we're printing the event and we're printing the prediction. So here's the event metadata and then here's the prediction. And that's it. So once you have your model, you can do this we do this at near real time. You could do this in batch. You could do this daily, right? So you could have a sim app, right? That every hour you collect all the PowerShell events that you've seen, analyze them, and if anything are classified malicious, show up in the sim app, send you an email, whatever you want, right? And all this was done on my laptop, so you don't need powerful hardware at all. Very minimal hardware, in fact. So it just depends on what you want to do. If you want to get streaming in real time and you want to do make sure that everything's tracked correctly, that's a lot more engineering. But I mean, like at the beginning of this, I'm like, worst case scenario, every day I'm going to run a report across all the events that I've seen and just create a report and send an email. And that's like the worst case scenario. You do that same thing every hour, send an email every hour, whatever you want to do, whatever works for you. But that could be a challenge. The engineering could be a challenge depending on your environment. Some places are very averse to any type of engineering like that. Some places you have people that can do it. So we're talking about some pitfalls. Now, admittedly, the pitfalls are where I'm weakest at. As a security practitioner, I'm like, this works awesome. In my opinion, like, what are we going to do next? But there's actually a lot of pitfalls here. So one, in machine learning, overfitting your data. So if you test your accuracy on the training data, it's called overfitting because you're training it. You're saying what's bad look like, and then you're also getting your accuracy from the data that's been trained on. So you're saying you're overfitting to that data. Creating a model using all of your labeled data will most likely give good accuracy and test very poor. not enough data, lack of diverse data. So this is kind of a problem we had at first. At first, I'm testing on a very small scope of data, very narrow. Once we expanded that out, we started to realize that the way organizations run PowerShell are very different from one place to another. And then there's bad data. We had some instances where we actually mislabeled the data because, like I said, we really read through 5,000 pieces of logs. And so you're going through there. We actually have a setup. You can click, malicious or benign, and we accidentally click one the wrong way, right? So that's one. Another one too is when we were using the Palo Alto test encoded event data. When you decode the events, some of those were like printing hello world and just putting up calculator. They were demo events. So those we automatically classified everything in there, and once we looked at that, we realized these aren't actually all malicious. So like some of these are really just like demos and that we didn't want to train our data on because it wasn't really legitimate. And then bad data, like I said, certain algorithms require data in certain formats. So some algorithms you can have variables say cat, dog, person, and 0, 1, 2, 3, and along with ratios. Some data, all your values have to be, or some algorithms, all your data have to be between 0 and 1. That's where I'm pretty weak. But basically, you look it up and you start understanding what type of data works with it. And eventually, once we settle on an algorithm, we figured this out and formatted our data respectively. The primary one we were considering with was overfitting. So our data was pretty good, and it was fairly thorough with the k-fold validation on a training set. But one of the issues we encountered was, if you notice that 2 of our values are hand-engineered predictors. So we have a list that we create of suspicious. We have a list that we create of malicious modules. That's our opinion. So when you're creating these, you kind of want to remove opinion as much as possible. 2, that has to be updated as time goes on. So we're like, well, if we've got to update this, kind of sucks. It's a little bit better than rules, but we still have to continually update these models. And every time we update this, we have to retrain we have to recalculate all the data and retrain the models. So that's kind of that's not optimal. And a lot of machine learning purists are like no hand engineered predictors. That's kind of a thing a lot of people they avoid as much as possible. Sometimes though, if you want to encode your expertise, you do need hand engineered models or predictors. So in some cases, it doesn't make sense. So another one's not enough data, lack of diverse data. The data was pretty good with the large, but there's still some new type of events, like the one I told you about, popped open Internet Explorer using PowerShell code we had never previously seen, and that was misclassified. So this shows up in reduced production accuracy, but it's really going to be unavoidable. We have almost as good amount of data as possible because we're pulling it from VirusTotal, we're pulling it from the internet, we're pulling it from a wide array of sources. So I believe at this point it's not perfect, but it's about almost as perfect as we can get. And the bad data. So here's what I mentioned, like the format that it comes in, should be a certain format. So I found out that some algorithms prefer normalized event data. So you can take, like I showed you my array of records that have some are ratios and some are just counts. Well, you can actually take that and normalize that. And what that does is take, those counts, so you might have up to like 32 malicious modules counted, some to 0. You can adjust every single value in there between 0 and 1. And so there's this normalization algorithm right here where it can do that. So basically what you take is for each value, so if your count was 16, you subtract the minimum. So if the minimum count's going to be 0, and you divide it by the max, so maybe the max is 32, minus the minimum, which was 0. What that provides is a number between 0 and 1. And so that converts your counts to between 0 and 1. And you can do that for any type of numerical data possible. This works in most cases. Looked it up, not every case. Some cases you do not want to do this. But for when I applied to the algorithms we were working on, it seemed like it was the best fit. And this also may be the reason why some of those original algorithms scored pretty bad when compared in 96 compared to the others. So I didn't go back and check them because we had pretty high accuracy to the point where I'm questioning the data. So we would just be doing a lot of work to get a little bit of gain at most. Not enough data, lack of data. There's not much I can do there. The bad data. So that was an easy fix. So we normalize all our data now. To the values of predictors. The way you normalize is part of scikit-learn and almost any machine learning toolkit. Basically, you pass that whole file that we have where it's called my predictors, and you pass it to this pre-processing function, and it just normalizes everything for you, spits out all the values in between 0 and 1. You can take a look more here at scikit-learn. Very well documented if you're interested. So really for us, overfitting was our primary concern. Another thing, we're hand engineering those predictors of what's malicious and what's benign. I looked at all malicious samples and said, okay, this is what I think is malicious. That's kind of overfitting because we're looking at the data, and I'm basically saying, here's how we can detect all the malicious data. So we don't want to constantly comb through this, and we address this by changing the algorithm and the predictors. We actually now, we use a tool to generate, instead of having a count of predictors, or a count of suspicious or malicious modules, we use a vectorization technique. So we take the events, we split them into terms now. So now we actually have like 2,000 predictors. And these are all the unique terms that we see in all of our PowerShell events. And if one is present for that predictor in that record, we'll put a 1 there. If it's not present, it'll be a 0 there. And from there, it's automatically learning. We're automatically generating the vocabulary to use, and it's automatically learning what constitutes bad and what constitutes good. So this way, it's automatic. It trains better. And we can define the vocabulary. We limit the vocab. You can use a regex. You can say, you don't want a predictor to be this huge base 64 string that you'll never see anywhere else, because that's not valuable. You want things to be, like word terms. So we have a regular expression that pulls out more valuable terms to use. And I'm going to kind of show you how to do that. So the text, it's called vectorization in scikit-learn. You have the count vectorizer. So basically, you pass it an event, give it some configuration options, and it'll just split that event into a list of tokens, and then we can do essentially word frequency analysis in the model. So here's an example of that. So here we have a list of these are just a list of terms, but you could think of this as a list of PowerShell events, right? So we have the quick brown fox, John, and then I have the. So here we say we're going to use the count vectorizer, so we have that object, and I'm going to say transform the sample, so all of this, into an array of the vectorizer. And then here I'm just printing it. So here we see from this list of events, so this is 5 term list, but this could be 10,000 PowerShell events. We have 5 unique terms. And so you see here there's 1, 2, 3, 4, 5, 6 events, which corresponds to each one of these as a row. So we have 1, 2, 3, 4, 5, 6 rows of data. And so here you see this appears in 4. So the quick brown, so this is row 4. So this 4 right here, so you see in almost all of them, we have 1. The last one you see it 2 times. Quick is in the 3rd column. So quick appears in the 2nd, 3rd, and 4th record, and so on, right? And so you can think of that as 10,000 rows of PowerShell events with 15,000 terms. So whenever you see this, instead of quick, this could be interpreter. Instead of brown, this could be and instead of fox, this could be shellcode, right? And so every time you see shellcode, it's going to give a 1 for that event, and it's going to learn on its own what's bad and what's good. And this also has the added benefit, I think, of determining, what terms predict good events. Because before we're just looking at suspicious and benign, we're not really looking at what terms indicate good events. So does that make sense? This is what I had the hardest part, and we kind of moved to this very late because we didn't realize we had that problem until we spent a lot of time updating the suspicious module list and stuff like that. So with this, we've had great success. We also use we use Keras now. Yeah, we use Keras now. It's kind of an engineering. So we use a neural network for that. So if you think of whenever you see AI, these neural networks, but essentially in scikit-learn, it's just called MLP classifier. It's just another classifier that's used. It's super configurable, right? Because you think of whenever you see neural nets, they have neurons and things like that. And so we do some sort of, we build out that architecture. But with Keras, we can use TensorFlow, which can be adapted to the cloud. We can output to Azure. We can output to AWS. So it gives us a little bit more freedom. The actual neural net algorithm works very well, we've noticed. So that's what we've gone with. So here we're automatically generating the vocabulary. We started using the neural net, and really the changes provide more stable and resilient results in production with less overhead. So even when we see false negatives, well, one thing we'll notice is we'll add it, if it's data we've never really seen before, like a type of malicious event we've never seen, we'll add it to the training set, and then new similar events will be processed as malicious. Even though they're not exactly the same, but they use the same techniques, it updates, and that's kind of what we want, right? We want to be able to quickly update. We want to identify things we've never seen before, and operate accurately. So in the end, right, we generated a highly successful model. I quickly iterated through different tuning parameters. We easily update with new samples, and we're constantly monitoring for false positives and false negatives. So any false positives, so if we predict something malicious and it's actually benign, that goes right to us. Any false negatives, so something that's from VirusTotal is predicted as benign, goes straight to us too for evaluation, just to determine is this a new, why do we think that this wasn't malicious. So here's some resources. I have a Jupyter notebook. This contains the data set that I showed here. Basically goes through everything I did right here, so you can do it at home if you're interested. If you have scikit-learn and matplotlib installed, it's just running the cells over and over, and kind of with a little bit of a markup description. The malware archaeology cheat sheet. This, if you have very little knowledge of like what's malicious or what's suspicious, how to configure PowerShell, what's important, that's the #1 thing you should go to, in my opinion. It's like 4 pages long, and it's just packed with all good information. Invoke and revoke obfuscation. Invoke obfuscation I use to generate a lot of samples, right? Here's a lot of crazy samples. Revoke obfuscation. So this is one thing why revoke obfuscation came out about Black Hat last year. Essentially, they're doing very similar to what I'm doing. They're classifying PowerShell, and so as I'm doing this earlier in the year, I'm like, oh crap! I saw this in Black Hat, and I'm thinking they're doing something very similar. I think it's a little bit different goal. They're looking for obfuscated samples. They use different methodologies, right? They're using I think C#. And they pull a lot of samples from GitHub and things. So that's an actual one to take a look at, and I think you can train it yourself on your own samples, things like that. It's kind of weird how you can be working on something and someone else can be also working on the same thing. But if you look at this, it makes sense, right? Because when you start looking at his invoke obfuscation samples, you're like, I can easily determine what's bad here, but it's hard to create rules. Why is that? And you start thinking, well, it's super long, super dense, the capitalization's messed up, there's all kinds of numbers, there's all kinds of special characters, and you start thinking, well, where do you go from there? And really, I think the next logical step's the classification algorithm. And then also, if you're looking at samples, here's the Unit 42 from Palo Alto. It has a ridiculously large quantity of encoded commands. The events themselves look very similar, right? Because PowerShell encoded commands all follow the same pattern. PowerShell exe -enc or some variant of that, right? -e -encode -encoded command, followed by a huge blob of base 64. But what's interesting is the decoded portions of the base 64 can vary significantly. That's one thing we do too is we don't decode or deobfuscate samples automatically, but if it's using encoded command, we decode that and then analyze it, because too often encoded commands used in legitimate processes. Strangely enough, it just seems weird to me. But then again, I've never really administered anything, so I can't. I guess I'm in no place to criticize. But it triggered so many. We thought at first, oh, we'll just investigate every false positive. It can't be that many. Turned out there was. So then we decode those automatically, analyze the decoded content, and then make a judgment. But if we see something that's like obfuscate with invoke obfuscation, we've never seen that legitimately. So if we ever see that, that's just an instant malicious. So one thing we have seen is doubly encoded commands for legitimate purposes. So we had one trigger malicious. So it's just an encoded command with a blob of text. What it decoded to was another PowerShell.exe with another encoded command. Then that encoded command ended up being like an update or like some sort of orchestration software. So we're like, wow, that's kind of strange that an administrator doubly encoded this. Like, I don't know if they're just messing with people or it's an accident or what. So that's about it. You guys got any questions? Any questions? Hi, Tish.
Hey, great talk. Just a quick comment. If anybody who's doing this sort of stuff, Wayne State University has something called Blurry Labs. It's a computer coding event free and open to the public. Next session is going to start January 22nd to February 2nd. It's on AI. The one after that is going to start on February 19th. It's going to be on AI and the Internet of Things. We'll have people from GE Labs, Detroit Labs, and Flywheel Labs. So it's not it.
Yep. Yeah, I went to PyData's in Ann Arbor too, which is a very cool. It's like a Python. Super smart people there. They're talking about time series analysis, neural networks, TensorFlow, things like that. But it's just strictly based on Python data analysis. So I'm trying to go there. It's all new to me. So all of this is really new to me. I kind of feel like as I'm going through this, I feel like when I first started in security, you start picking up everything. You're like, wow, this is all awesome. And then you start to realize you don't really know that much. And so, and 7 years later, I feel more confident in what I know in security. Now I feel completely not very confident in this. But I mean, with very little knowledge, you can implement something highly successful. It may not be strict in terms of academics, but in terms of production, it seems to work very well.
Questions? Comments?
You did great.
Thank you.